Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 3.8. A rectangular block floats in pure water with 0.5 inch above the surface and 1.5 inch below the surface. When placed in an aqueous solution, the block of material floats with 1 inch below the surface. Estimate the specific gravities of the block and the solution. Suggestion: call the horizontal cross-section area of the block capital A. Capital A should cancel in your calculations. So this is really similar to the last problem that we did, 3.7. If you have trouble following this solution, maybe looking at that solution will help clear some things up, and you'll be able to see a little more details of what's going on. All right, so I'll go ahead and get started here. 3.7. Hey, this is me from the future. I am just noticing that I wrote 3.7 here. It is actually 3.8. So we are doing problem 3.8. No need to worry about that. Let's draw a picture of what we've got. So we've got water here, and this is pure water, and we've got a block floating in the pure water. Okay. In the pure water, we've got a height here that I'll call height A, which is equal to 0.5. And then we've got a height here that I'll call that height W. And that is 1.5 inches. Okay. Okay, so now it's time for us to draw out the force balance and then also to make some assumptions here. So we're doing a force balance. Let's draw our block once more, but this time we'll draw it with the forces on it. Okay, so there's the force of gravity, and there's the force of the water buoyancy. And I am going to make an assumption here that the buoyancy of the block in the air is negligible compared to the buoyancy of the block in the water. And so there's no buoyancy force, even though it's in air. At least 0.5 inches of it is in air. Air is about 1,000 times less dense than the water, and so we'll just assume that that's negligible for this calculation. So okay, so that means that the force of the buoyancy due to the water is equal to the force due to gravity. Okay. From Newton's second law, we know that force equals mass times acceleration. And in this case, the acceleration is only due to gravity. And so the force equals the mass of the water displaced times the acceleration due to gravity. And the force of the weight equals the mass of the block. We don't know what the block is made out of, so I'll just call it B, is times gravity equals the force. Okay. Then these two terms cancel out, and we know that the mass equals the volume times the density. So we'll convert these into volumes and densities. So we got the volume of the water displaced and the density of the water. And then we've got the volume of the block times the density of the block. It gave us a hint in the problem statement to break up this volume into cross-sectional area times the height. And so the heights will be variables that we know, and we'll just pull that out of the cross-sectional area. So the volume of the water displaced is equal to the area, the cross-sectional area of the block, times the height of the block in the water, so HW. Okay, and then that still times the density. And on this side, we have the total volume of the block, which should be the total height of the block. So the cross-sectional area times the total height of the block times the density of the block equals the mass of the block. Okay, we could call that HB as well, I guess. We see that the cross-sectional areas cancel out. So we're just left with the height in the water times the density of the water equals the height of the block, total height, times the density of the block. And what we want to solve for is what is the density of the block. Okay, so let's solve for the density of the block. That equals the height in the water, density of the water divided by the height of the block. Okay, so now let's substitute in all of our numbers here and solve for what that is. Okay, so that equals 0.75 grams per centimeters cubed. All right, so that's the density of the block. Now let's do the density of the solution. It's an aqueous solution. So aqueous solution means it's a mixture. So it's water with something in it. They don't tell us what it is, but whatever it is changing the height of the block. So it changed the density when they mixed the water with whatever this other element was. And so we just do this calculation backwards, basically, to figure out what the height of the block in the solution is. So basically doing the same thing, all of the same equation, mass balance, force balance, everything applies still, except instead of having it say water, we'll swap water with solution. Okay, so everywhere that it says water, we'll change it to say solution. So the height of the solution, density of the solution equals the height of the block times the density of the block. Okay, so now we're solving what's the density of the solution, which equals the height of the block times the density of the block divided by the height in the solution. Now it told us that when placed in an aqueous solution, the block of material floats with 1 inch below the surface. Okay, so that means we have 2 times 0.75 grams per centimeter cubed over 1. So that means the density of the solution is 1.5 grams per centimeter cubed. And let's check to see if this makes sense. If the solution is more dense than pure water, then the block should float even more on the solution than it should float on the water. So it should be higher out of the solution. And let's check. So for water, it was low in the solution, 1.5 inches. Most of the block was in the water. But for the solution, the height was 1 inch. So the block came out of the water about half an inch. And so that makes sense that the block is sitting in a more dense solution on the second part. Okay, well that is it for problem number 3.8. Thanks for joining me, and if you have any comments or questions about how to do this problem or questions about the solution, please just put them in the comments below, and I'll be happy to get back to those and help answer some of your questions. If you have any other questions that you need help with from this book or from another engineering discipline, let me know, and I will see what I can do to help out and make another video potentially. Thanks for joining me, and I hope to see you in the next video. Thanks. Bye.